both the signal and the system. That is a point that needs to be emphasized. You see, now for example here, what does the Fourier transform do from the perspective of the third point? You see, the Fourier transform takes this whole situation, you have this time domain interpretation. So you have, see, it alters the domain. So you have a time domain representation where you put in xt, convolve it, so it's an LSI system, you convolve it with ht and it results in yt. This is convolve, right? On the other hand, in the frequency, the same thing can be viewed in a different perspective, right? One can view it in a different perspective. So one can view it as putting in x omega. Again, there is an LSI system with, now we will give it a name, we will give this quantity a name very soon. With the impulse, the Fourier transform the impulse response given by h omega to produce y omega. And here the operation is multiply. So from convolve, the system that convolves here multiplies in that domain. So it also, as somebody pointed out, there is also a transformation, there is also a change in the way the system behaves in the different domain. An operation of convolution translates into an operation of multiplication. We shall similarly see what happens to other operations later. For example, if you happen to shift this input, what happens to the corresponding, and so on. We'll come to that interpretation later, right? But the point is, it also changes the way in which the system operates. Sometimes to convenience, sometimes not to convenience, right? So you see, it's in the context of LSI systems, it's certainly very advantageous to use the Fourier transform. And it must also be understood that sometimes it could be possible that this is invertible, in the sense that if the Fourier transform exists, there is a one-to-one correspondence. But the Fourier transform may not exist for all xt. So it might happen that only a limited class of these can be put into a one-to-one correspondence with these, right? So what I'm trying to explain to you here is that, in the beginning of the course, we had two levels in the hierarchy. We had signals, we had mappings from signals to signals which were systems. Now we have one step higher. We could think of transforms as mapping on signals, but we could also think of them as mappings on systems or mappings on the whole signal system context. So it's one step higher in the hierarchy of our discussion, right? That's what transforms are. They're one step higher in the hierarchy of discussion, right? Signals, systems, and then transforms. But of course, transforms also pose or also behave as systems. Like the Fourier transformer can behave as a system when acting on a signal. But the Fourier transform in total can transform or change or remanifest the whole context of signal and system in a different way. We shall see that the same thing will happen with the Laplace transform later. Or we will also be studying the Z transform later. It shall also happen in the context of the Z transform. It remanifests the whole way in which we look at the signal and system context. Yeah? So now with this background or with this discussion on the philosophy or the context of a transform, let's go down to looking at the Fourier transform in greater depth. Now we've been saying all the time, if the Fourier transform exists, if the Fourier transform is defined and so on, right? And we've been postponing the discussion of, yes, Chaitanya? Does it always change the region of support? What do you mean by region of support? Okay. That's a good question. Is it necessary that the domain, the region of support is not changed? No, it's not necessary. In fact, we'll see later when we talk about discrete time systems that it actually changes the region of support. Does it always change? No, it doesn't always change. For example, in the Fourier transform, the domain of support is the same. It's the real axis for time and real axis for frequency. There would be a No, but even so, but then you see, okay, the question is, if does it suppose this, it could happen that the Fourier transform is non-zero only for a certain part of omega. That can happen, but that means that the Fourier transform is zero at other places and is defined. So the domain, you see, it's like saying, well, a signal is defined only on the interval between 1 and 2, and the signal is non-zero on the interval 1 and 2. They are two different things. A signal can be defined on the whole real axis, but could be non-zero between 1 and 2. Or it could be defined only between 1 and 2. Now the Fourier transform, see, for example, the Fourier transform in most contexts is defined all over the real axis, right? Both in time, in frequency, right? But it could happen that, the Fourier transform is non-zero only for a certain interval of the frequency axis. That's no problem. So you see the domain of support, if you say that, okay, now that brings an interesting question up. Suppose you have a function, in fact this leads us to a problem which I'll put as a challenge to the class. Suppose you have a function which is limited in its domain of support in time. That means it is non-zero only for a certain interval of time. Can we at all say something about its domain of support in frequency? Right? It's not a trivial question. Right? Since Chaitanya brought up this question also came to my mind, and I thought I should put it across as a question which you could ponder over. It's not a trivial question. It's a non-trivial question. I shan't give you the answer. Right? What I mean by the answer is it always true that, can we say something universally? That, if the domain of support is restricted in time, it never can be restricted in frequency, or it is always restricted in frequency, or it is sometimes restricted in frequency and sometimes not restricted in frequency. Well, that's the question. Which of these is correct and why? Okay, that's the question. Anyway, so coming back to this discussion, yeah. So you see, now we've been postponing all the while. Are there any other questions? All right. So we've been postponing all the while this discussion on when the Fourier transform exists. What are the conditions under which the Fourier transform converges and so on. Now we'll come down to addressing them. In fact, let's begin with the Fourier series first. Let's take an example of a function. Suppose we have a function of the following nature. It is 1 for the first half interval of t by 2 and minus 1 for the second half interval of t by 2. And it is periodically repeated after that. Right? So the function is periodic with a period of t. Now we can write down its Fourier series representation. How do we write down its Fourier series representation? We would take, in fact, let's write down the expression for the Fourier series coefficients. The coefficient Ck would be given by integral from 0 to t by 2 e raised to power minus j k 2 pi by t times t dt minus integral t by 2 to t, the same thing. This whole thing is divided by t. this integral is very easy to evaluate. There is no problem. It is just an integral of the form e raised to the power a t dt. It is very easy to evaluate. I do not need to evaluate it and show you. But the point is, you see, you may now consider the inverse. So, we may write down the series summation on k, ck e raised to the power j k 2 pi by t times t. K runs over all the integers, right? So, k runs from minus infinity to plus infinity. Now, this is a this is a sum of highly continuous, in fact, analytic functions. Each of these functions e raised to the power j 2 pi by t times kt is analytic in the sense that it has an infinite number of derivatives. So, it seems very unlikely to us that this quantity will give us something like this, and we are quite correct, because if we happen to write down this summation with a finite number of terms, so if we choose to truncate this summation, so we consider the following. Instead of considering this from minus infinity to plus infinity, we look at the summation from minus n to plus n and take the limit as n tends to infinity. What are we doing? We are including more and more terms in the summation. Now, I would actually encourage you to carry out this experiment. Nowadays, we have this software called MATLAB. And in MATLAB, one can do these kind of experiments quite conveniently. In fact, some of the versions of MATLAB also have a nice demonstration of this phenomenon, which I am going to explain. Right? Anyway, the phenomenon is as follows. You see, as we include more and more terms, we observe the following. If you take a certain number of terms n in the summation, a finite number of terms, then the sum looks something like this. And of course, I am saying you take the terms symmetrically. Now, why do you take terms symmetrically? Because the function is real. So, you see, for each, if you want sine waves, then for each sine wave, you need a corresponding positive value of k and a corresponding negative value of k. And the two together produce a sine wave. In fact, in general, for a real function, it is very easy to show that c of k will be equal to c of minus k complex conjugate. We reasoned this out before as well, right? Because the idea is that you have two rotating complex numbers and they must have the same amplitude of and equal and opposite frequencies of rotation, and they must start from opposite phases. Then they will produce a sine wave. So, that means that they must be complex conjugates, right? Now, the point is that, if you take a finite number of terms, the sum looks something like this. I am drawing it only over one interval. This is what the sum looks like. If you take an even larger, now you see one point to be noted. What happens at the point of discontinuity? At the point of discontinuity, the sum approaches 0. What is 0? 0 is the average of the two extremes of the discontinuity. And this is universally true. It is always true that at the point of discontinuity, the sum of the series approaches the average value of the two extremes of the discontinuity. All right? What is more is the following. If you increase the number of terms, the following is observed. So, let me amplify it here to show you what I mean. So, this was the original function that you are trying to represent as a Fourier series. And this is what so if you increase the terms further, this is what you will observe. You will observe very small oscillations here, but a so the idea is, when you increase the number of terms, these oscillations in this part of the function reduce. But at the point of discontinuity, there are two problems. One is, at the point of discontinuity, still the function tends to the average. And worse still, at the two sides of the discontinuity, you have a tremendous deviation from the function. This is this part, this tremendous deviation from the function. And all that happens is, as you increase the number of terms n, this deviation doesn't go down after a while. The extent of deviation, this height of deviation doesn't come down. It just remains the same, but it gets compressed. So, the deviation is on a smaller and smaller and smaller interval. Now, this is something which a lot of physicists noticed, when they actually started using this idea of decomposition of the periodic class of functions, and Gibbs gave an explanation to it. And therefore, this phenomenon is called Gibbs phenomenon. What does the Gibbs phenomenon say? It says that when you have a point of discontinuity, and if you keep taking a larger and larger number of terms, the convergence of the series, the Fourier series, is to the average of the two extremes of the discontinuity, but on either side of the discontinuity there is a deviation from the ideal value, and that the extent of deviation does not go down after a certain value of n, or it tends to stabilize. So, there is always that significant deviation. The only thing that happens is, as n grows larger and larger, this deviation starts getting compressed towards the discontinuity. Now, what are the implications of this? Well, you see, does this mean that the function that we represent by a Fourier series is not really the function that we are trying to analyze? Well, in what sense? That's the question. It's not really equal, we agree. It's not really the same function. But what is the difference then? The difference is at certain isolated points. So, when we talk of equality of functions now, when we say one function is equal to another, or a series is equal to the function, we need to broaden our idea of equality. Sometimes we cannot talk about point-wise equality, right? We can talk about weaker kinds of equality. One weaker kind of equality is the following. Suppose you look at the difference between this approximated or this series summed function and the original function. So, you plotted the difference function. You looked at the magnitude squared of the difference function and found the area under the magnitude squared of the difference on one interval, t. Right? What is the interpretation of that? If you look at it carefully, it's like saying, I have xt I have x approximate t, which I will denote by x tilde t, right? So, I have x tilde t, it's an approximation to x. How do I get this approximation to x? By keeping on summing the Fourier series for more and more terms. I look at the magnitude squared of this difference and integrate this over one period. Right? Now, in a certain sense, see, if you now for the moment, suppose you define both the functions only over that one period, xt and x tilde t. Suppose you define them only on that one period, forget about the rest. Can we interpret this quantity in the language that we have been speaking in the last couple of lectures. And in fact, can you see that if you think of xt minus x tilde t as a signal in itself, you could call it et if you liked, or xet. You would call this xet. The error signal, right? Then mod xet squared dt is nothing but xet into xet bar dt. So it's like a dot product of xe with itself. Now what does the dot product of xet with itself give you? The magnitude squared in our language of vectors. So it's like a magnitude squared of the error signal. Right? If you think about it, if you think of the error signal as a vector, it's like the magnitude squared of that vector. Right? What is further is that we are saying that, you see here, this error signal is the difference. Now if you take two vectors, you see if you have two vectors, think of two two-dimensional vectors. And think of their difference. How do you get their difference? This, so let's say A minus B, right? A and minus B, right? So it would be this. Right? So difference, the magnitude squared of the difference is what we are calculating here. It's like a distance between the vectors. This is like a distance between the vectors xt and x tilde t. Right? So the moment you have a dot product between two vectors, you can also have a corresponding magnitude, and from the magnitude you can have a distance between vectors. Now it is in this language that we can make a statement about the Fourier series. It can be shown that for a wide class of, if the periodic signal has finite magnitude in the following sense. Take the periodic signal. Look at only one period of the signal. That's a new signal with only one period. Look at the magnitude squared of that one period. If it is finite, right, then in a wide class of situations, the Fourier series representation, when we keep increasing the number of terms, approaches an x tilde t whose distance from this approach is 0. Okay? So the idea is that this equality between xt and x tilde t is the sense of distance. It might be possible that at individual isolated points there is a problem, like the points of discontinuity. But those problems get isolated to single points. So when you look at an integral, under an integral, there is no problem. So when sometimes we need to broaden our idea of equality. So this idea of equality of the series, the function xt and its Fourier series, is not equality in the sense of point by point. It's an equality in the sense of distance of vectors. The distance tends towards 0 as you increase the number of terms in the series. Now that's for a wide class. That's still. So one thing that is needed, of course, is that, in order for this to happen, the first thing that we need, of course, is that the function has a finite energy if you isolate one period. Right? So, see, one way to think of it is, for a periodic signal, if you take energy over one period, it's like the power. Right? When you have a periodic function, the energy in one period is the power. So you can say a periodic signal with finite power, right, has this property. Now anyway, is that all? It turns out that that's not all. Is this enough for the function to be represented correctly by its Fourier series? It's not all. There are two more conditions that we require. In fact, Dirichlet, as I said earlier, Dirichlet was the one who studied this problem in great depth. Yeah. So came out with 3 conditions that were of importance in the decision as to whether the Fourier series was a correct representation or not, right? He showed that a set of sufficient conditions were the following. Condition number 1, absolute integrability. That means the integral mod xt dt is finite. Condition number 2, bounded variation. I will explain what that means. And condition number 3, finite discontinuities, finite number of discontinuities. Over finite intervals. Now, what we are talking about here is a set of, I will explain these conditions one by one, they need explanation, right. We are talking about a set of conditions that are sufficient in order that the Fourier transform and inverse Fourier transform relationship are valid. That means if you take the Fourier transform in the context of a function that is not periodic, or if you take a Fourier series in the context of a function that is periodic, and then if you take the inverse gets you back to the original function as understood in the sense of distance, right? That except at isolated points, under the, if you look at the distance between these two functions thought of as vectors, the distance tends to 0. Or except at points of discontinuity, the convergence is to the correct value of the function at almost all points. What do we mean by almost all points? All except certain finite isolated points. Now, for that, what are the conditions? Well, the first condition is absolute integrability. Absolute integrability means the following. You see, if you are talking about one period, if you are talking about a periodic function, then here we restrict this integral to one interval. And we look at one interval of the periodic function and find out whether the integral of the absolute value of the function over that interval is finite. Now, when might it not be finite? Suppose, for example, you take the function 1 by t over the interval from 0 to 1 and repeat this function periodically for every multiple of 1. 1 by t tends towards infinity, and in fact, if you integrate this, the absolute value of this is not integrable over the interval 0 to 1. So, this is an example which does not satisfy criterion number 1. Right? Of course, the moment it doesn't satisfy absolute integrability, we don't even need to check the other conditions. So, absolute integrability is like a first shortlisting criterion. Now, it may satisfy absolute integrability, but it may not satisfy the second requirement. Let's look at the second requirement. You see, now 1 by t is not absolutely integrable. But suppose you take a function which is bounded on this. So, suppose you take sine 1 by t. Now, sine 1 by t is a highly continuous function. It is an analytic function over the interval 0 to 1 if you exclude 0. Right? But it has a problem with criterion number 2. What does criterion number 2 say? It says bounded where it means that if you look at a finite interval, there must be a finite number of maxima and minima. Right? So, the number of points at which the function reaches a local maximum and a local minimum must be finite. If you look at the function sine 1 by t, as you approach 0, the maxima and minima start getting compressed infinitely. In fact, there is an infinite number of maxima and minima in the finite interval 0 to 1. Is that clear? Right? So, therefore, this function is said to have unbounded variation or an infinite number of maxima and minima in a finite interval. Right? So, although the function is absolutely, see, why is it absolutely integrable? Because the function is definitely bounded by 1. And at best, if you look at the integral of the function on the interval of 1, it cannot exceed 1 because 1 into 1. So, the function must be absolutely integrable. But it is not a bounded variation. Now, so these are, it's like if it has passed through, if it doesn't pass through this gate, of course, it doesn't pass through the other gates. But if it passes through this gate, then this could be a stopping point like this. But now the third stopping point, you see, it could pass through this gate, it could also pass through this gate. But there could be a third stopping point. The third stopping point is that you must count the number of discontinuities. See, a function could be absolutely integrable. It could have a finite number of maxima and minima. In fact, it might have only one maximum. Let me give you an example. Let's take the following function. Let's define it over 0 to 1 again, right? Now, let's keep subdividing this interval into subintervals of half the size or 1/3, either way. So, let's take a case where you take 2/3 and 1/3, right? So, you have 2/3 and 1/3. Now, in the next step, you again divide this interval into 2/3 and 1/3, right? So, where will it come? I mean, you have 1/3 into 2/3, so 2 by 9, right? So 4 by, so anyway, this is 6 by 9, right? So now I think it's not too difficult to visualize. At every step, divide the interval into 2/3 and 1/3 and have a discontinuity at the 2/3 point, right? So you have a situation like this. One can keep reducing the value by a factor of, by a constant factor, right? So you could keep reducing the value by a constant factor. So each time you take it to 2/3 of the remaining interval and then bring it down by a constant factor, right? But that constant factor also exponentially decreases. Can you see that, right? So it's like a step function, it's like a stepwise function which has an infinite number of steps, and as you go towards one, the number of steps also keeps on going towards infinite. I mean, the steps grow closer and closer, and the step size also keeps going smaller and smaller. Right? Can you visualize this function? Now, this function is definitely absolutely integrable. Its integral cannot exceed this into 1. Suppose this value is 1. The integral cannot exceed 1. This function has bounded variation because there is only one maximum really. But the function has an infinite number of discontinuities. There are as many discontinuities as the point at which a step occurs. Right? And therefore, this function also does not satisfy the third criterion. And that illustrates what we mean by the sufficient conditions that Dirichlet posed. Now, if it passes through all the three gates, so if a function, see, if you are talking about a periodic function, then you need to investigate over one period. If you are talking about an aperiodic function, that means a function which, has, if you are looking at the whole time axis, then you need to look at every restricted interval, right? So, what is the requirement on the function must be absolutely integrable over the interval of interest. So, if it's a periodic function over one period, or if it's an aperiodic function over the entire real axis. For every finite interval, there must be bounded variation. For every finite interval, there must be a bounded or a finite number of maxima and minima. If these three criteria are satisfied, then the Fourier series or transform relationships, are they are consistent with the inverse Fourier series and transform.